everyone. Welcome to another Tech Talk session. So as you can see, I will be talking about lexical analysis today. So before we start off, I want you guys to look at this slide and think of how you would describe these different groupings of characters. So for an example, I'm pretty sure most of you would say characters like this would be operators. Something like this would be a word. These would be numbers. And let's just say for now that these are symbols. And finally, this would be an emoji. So what most of you just did right now intuitively, that is sort of like coming up with a common label for a particular group of characters. That is like saying, okay, I think this group of characters would qualify for a word, or this group of characters would qualify for a number. So that process is basically like a high-level understanding of what lexical analysis is really about. So before I move on, so this is completely relevant to the presentation, but these two actually happen to be movie titles, so if any of you guys get bored during the session, you can try to figure out what they are. So the formal definition of lexical analysis is that it is the process of converting an input program from a stream of individual characters into a stream of tokens. So you can use the terms lexical analysis, lexing, or tokenizing interchangeably because they pretty much mean the same thing. So lexical analysis also happens to be the first stage of the compilation process of input program that is basically written in a high-level language like C or C++. So the program which performs lexical analysis, you can call it a lexer or a lexical analyzer or a tokenizer. Let's just say that we have a file which has an input program written in a language like C. So as far as the lexical analysis is concerned, this file is nothing more than a stream of characters. So the whole point of lexical analysis is converting this sort of bare-bone and primitive stream of characters into a stream of meaningful characters, meaningful tokens. So what I mean by that is those stream of tokens should be meaningful within the language that we're trying to analyze. So if we do have the source program and we have the lexical analyzer would look at this input file and categorize this source program into various types of tokens. So specifically in C, these token types can be things like keywords, identifiers, operators, and so on. So these are some of the basic terminologies that you come across when you talk about lexical analysis. So first we have a token. So a token is the smallest element of a program which is meaningful to the compiler. A lexeme is a part of the input stream that qualifies for a certain type of token. So a lexeme is pretty much an instance of a token. And a pattern is the set of rules that describe a token. So just to give you guys an example, so in the previous slide, if we take something like the word count, so count would be the lexeme that qualifies for the token type identifier. And since a pattern describes a token, we can just simply say the pattern which describes an identifier in C language is something that starts with an alphabetical letter or an underscore and is followed by one or more alphabetical letters or digits. So I hope you guys understood the difference between each of these terms. So this is the basic architecture of a lexical analyzer. So once we have the source program and when the parser issues the get next token command, the lexical analyzer would read the input file character by character until it comes across a lexeme which would qualify for a valid token. And when that happens, the lexical analyzer would basically just pass the token to the parser. So this process will continue until you come up with this bunch of tokens. So when you have this stream of tokens, you can just hand it over to the next stage of the compilation process. So for the compiler, from that point onwards, the compiler can completely forget about the original input file. So this is actually a good thing for the compiler, because the original input file can contain a lot of noise like white space or comments and things like that. So basically the lexical analyzer makes the life of the compiler much more easier. So at the bottom of the slide you can see something called the symbol table. So the lexical analyzer and the parser actually work together to construct this symbol table, which is a data structure that contains information which is used in different stages of the compilation process. So usually each entry in this table would be the lexeme of an identifier and various attributes related to that lexeme. So these attributes could be things like the type of the lexeme, the scope of the lexeme, or things like the number of bytes of storage it needs, things like that. So during the lexical analysis process, an entry would be made for a lexeme, and all of the associated values, attribute values of that particular lexeme will be filled progressively in the subsequent stages of the compilation process. Now that we've kind of understood the architecture, all in all, what does it mean to be a token? So I mentioned in one of the previous slides that a token should be meaningful within the language that we are considering. So basically, if we want to come up, or if you want to construct a lexical analyzer, if we were given that task, we should actually ask for this well-specified document that would tell us what it takes to be a token in that particular language. So basically in C, these are the different types of tokens that you can come across. So there are 6 categories, and if you look at each of these categories, they are very well defined, and there's no ambiguity or uncertainty among any of these categories. So because of this clear-cut difference, it's actually sort of impossible that someone would mistake something like, let's say, an identifier to something like an operator. So in that document I just mentioned, and if we consider the programming language C, that document should tell you how to identify each and every one of these token types uniquely. So if we were to construct a lexical analyzer, what we would be basically doing is reading an input file character by character and checking for various constructs within that language. So if we take, let's say we take something like a C lexical analyzer and a Pascal lexical analyzer, the main difference between these two would be the set of rules that define how you can identify each of the tokens defined for that particular language. Does that make sense? Okay. So I said that to come up with a lexical analyzer, you need this document that tells you what are the rules you need to follow to identify these tokens. So this rule set is actually included in that file called the lexical specifications, which is shown at the top. And then you have something called the lexical analyzer generator, which is a tool that will take in the specification file you provide and convert that into the lexical analyzer. So then from that point onwards, the lexical analyzer will take in the source program you provide and tokenize it. So the lexical specification or the lexical specification file for any programming language would consist of information about identifying each and every one of the tokens that are defined for that language. And you use regular expressions to write these lexical specifications. That is, you use regular expressions to write the rule sets to identify each and every one of the tokens. which is why it says here that the regular expressions describe the lexeme and map them to the relevant token. So these are some of the examples of how you can define regular expressions for different types of tokens. In this case, tokens like keywords and identifiers. So the regular expression for a keyword would basically be the same as the keyword. So for an example, if you come across a lexeme and you want to see whether it qualifies for the token type keyword, you would basically be matching that or checking that lexeme against each one of these regular expressions shown there, and seeing if you can come up with a match. So if there's a match, that means that lexeme would qualify for that for the token type keyword. So for an identifier, the regular expression is a bit more tricky, but it's still simple. You can simplify the process by first defining a regular expression for a digit and then a regular expression for a letter, and then you can combine these two to come up with the regular expression for an identifier like this. So basically this regular expression says that an identifier starts with a letter and can be followed by one or more letters or digits, given the definition for the regular expression for a digit and a letter. So you can represent the same regular expression using a transition diagram like this. So I'm not going to explain that because it's pretty simple. So before I move into the demonstration, I sort of want to sum up the different types of roles that the lexical analyzer is able to perform. So first of all, we have tokenization, which is basically what I've been explaining for the past few minutes. And then the lexical analyzer is capable of removing white space and comments from the source program. And the lexical analyzer is also capable of generating the symbol table. And it can also track the source coordinates for each token, which in turn helps this last point, which is reporting errors encountered while generating tokens. So this slide pretty much summarizes what are the different functionalities of the lexical analyzer. So do you have any questions up until now? Okay, then I'll get into the demonstration. So for the demonstration, I have two examples, and these are pretty simple and pretty basic. So so for the first example, let's say I want to write my own programming language, and in this programming language I only want two types of tokens, words and digits. So if that were my requirements, my lexical specification file would look like this. So for any lexical specification file, there is this predefined format where you have three sections. So the first section shown here is called the declaration section, and in this section you would normally put your include statements for library functions, or define your function prototype declarations and other optional settings. And the most important section is the second section, which is called the translation rules section. So this is the section where you would define the regular expressions or the rule sets to identify the different types of tokens defined for your language. So since I said that my programming language has only two types of tokens, you can see there's one for words and another one for numbers. So basically in this section there is also a format you follow. So first you would state the pattern or the regular expression, which is then followed by this action block, which would basically tell you what to do if you come across that type of tokens. So just to give you an example, so this is the regular expression I've defined to identify a word, and this is the action block which I want to execute if the lexical analyzer that I'm trying to construct comes across a word in that particular input file. And in the same way, I've defined a regular expression to identify a number, and this is the action block that I want to execute if I come across a number like that. So these regular expressions are just something I've written to ignore white space or any characters that doesn't fall into either numbers or words. So the last section of the lexical specifications file is the auxiliary functions section, and this is where you would basically define the functions you use in the translation rules section. So I've defined the function I've used in the translation rules section, the display function. I've defined it in this last section, and you also have the driver function, and here I've just written a method to sort of read an input file. So if I try to, so I'll be using a tool called Flex, which will be my lexical analyzer generator. So what that would do is, so if I compile this specification file that I just showed you right now using this tool called Flex, that would give me an output file. This output file, which is a C output file, and wait, I'll show you what it looks like. So this is pretty much the converted specification file by the Flex tool. So this stuff I won't be getting into detail, but I just want to show you the last bit. So you can see that this section is exactly the block that I defined in the last section in the specification file. So all the other sections get converted during the compilation process, but this section in the specification file would be copied as it is to the output file. So yeah.
There are large sections where you those try to take the most regular expressions. I saw some digits 0, 1, 2, 3. Yeah, those so your previous that .py, the specification file, it also looked like the C program, right?
Yes, but it's not pure. Yeah, it's not pure C. Okay. But the last section is actually written in pure C.
Yeah, that is going to get copy pasted.
Yes.
And the regular expressions you had written in the specification file, do they get translated to manually written, like handwritten, not handwritten, like auto-generated, complicated C code which is capable of detecting that pattern?
Yes, something like that. So that is what happens. So the rest of the file would be handling that particular section in the specification file. Okay, so so now that we have this output file which is written in C, if I go ahead and compile that file, I would be getting this executable file which will basically be my lexical analyzer that I just constructed using the specification file. So since I said that my lexical analyzer should be able to identify the two types of tokens defined in my programming language, words and numbers. So if I try to feed, let's say, a text file which So this sample text file would have both numbers and words and other characters. So you can see that the lexical analyzer was actually able to differentiate numbers and words while ignoring other kind of characters like punctuation or special characters and things like that. So do you have any questions up until this point? Okay, so I'll get into my second example. So this is pretty much the same as the previous example, but what I'm trying to do is I'm trying to mimic the C programming language and how the specification file for a C programming language would look like. But this is a very basic and naive way of doing it. So I just wanted to show you this, just for you to get an understanding of how it works. So the first section is not that important. So this second section, where I define my translation rules, I've defined different regular expressions for keywords, integers, identifiers, and so on. So if you look at the section I've defined for keywords, this is just a subset of the number of keywords you have in C. So you have around 32 keywords. So here I'm just using only a subset. So I've defined these different types of regular expressions for the most common, actually the 6 types of tokens you can find in C. So the auxiliary functions section is pretty much the same as the one before, where I'm trying to read an input file.
On a realistic definition file, what do you call that? Specification file. Now for your auxiliary functions, you have done like printf, right?
Yeah.
But for a realistic specification file, they would contain some real code to send that piece of information to another file, like as part of the compilation process.
Yes. So so basically in a real life scenario, the lexical analyzer, if it comes across single characters like parentheses or plus marks and stuff like that, it would just output an integer code representing that particular character. But if it was some complicated group of characters like an identifier or keyword, it would send the integer code identifying that token type, as well as a pointer to the symbol table where you have the variable, as in the lexi. So just like before, if I go ahead and compile this specification file using flex, I would get another C output file. I won't get into details as to what's in it. And if I compile that output file, okay, so in this example, what I'm trying to do is I'm trying to construct a lexical analyzer which is capable of identifying the different types of tokens in this simple hello world program which I've written in C. So now that I compiled that C file, I will have this executable file which will be my lexical analyzer, and if I feed in my hello world program, you can see that it was basically able to identify the different types of tokens. So you can see there's keywords, identifiers, special symbols, even things like multi-line comments or strings, things like that. So you can come up with a more complex lexical analyzer which covers a lot of scenarios, but this is just for the demonstration. So yeah, that pretty much covers what I wanted to talk about today. Do you guys have any questions? Okay, if you guys don't have any questions, thank you.